Okay, so we're going to continue with the sketching of polar curves. So this example I left as homework from last time. Did anyone try it out? Some did. Okay, no, let's see how we do it. So we're going to do a little bit of side working to see what our points are. Then once we get the points, we just connect the dots and that gives us our shape. Okay, so what does this look like? So let's say we've got r and theta. So sine theta, we know what that looks like, but the +1 just means we move everything up. So it's going to look something like this. Okay, so we've got our important angles going along. So 0, pi over 2, pi in the middle, 3 pi over 2, and 2 pi. Okay, again, you can fill in more angles if you need. Okay, you don't need all of them. But if you have enough points to connect the dots, then that's all you really need. So let's write out what these values are going to be. So r of 0, that's going to be 1. R at pi over 2, that will be 2. R at pi, that will be 1 again. R at 3 pi over 2, that will be 0. Okay, that's where it goes down to the bottom there. And then r of 2 pi, that will be back to 1. Okay, so we've got this idea of the radius starting at 1, then the radius gets larger to 2, back down to 1, then to 0, and then back out to 1. Okay, so that's the idea of what we need to plot going around. Okay, let's fill in our axes. So we've got something like this. Okay, again, you don't need to fill in all of the angles there, just the ones that you need. But here we've got 0, pi over 4, pi over 2, 3 pi over 4, back to pi, 5 pi over 4. Okay, bottom one, that's 3 pi over 2, 7 pi over 4, and then back to 2 pi, but we already have that at 0. Okay, what about the concentric circles? Well, looking at the radius, we're going to have one of the radii here being 1, and then this other one is 2, so we only really need 2 circles. So let's say that has radius 1, and then we've got a bigger one that will have radius 2. Something like that. Okay. So just a note for tests and exams, you will need to draw this. Okay, so that will not be provided to you. Okay, so, try to do it freehand neatly. If you can't do that, right, you got your compass and all of that to draw the circles. Okay, but that won't be given to you. Part of the marking is drawing that. Okay, let's put in our dots. So at the beginning, when the angle is 0, the radius is 1. So angle 0, radius 1, we're going to be over there. That's our first dot. Next dot, at pi over 2, the radius will be 2. So pi over 2, that's the vertical. Radius 2, that means we're on the second circle. So we're going to be over there. Okay, next one. At pi, the radius is 1. So at pi here, we go out to the left at radius 1. So we got a dot over there. Okay. Then at 3 pi over 2, so that's the angle going down. The radius is 0, so we're back at the origin. Okay. And then finally, at 2 pi, we're back all the way around. The radius is 1, so we're back to that dot that we started with. Okay, so how are we going to connect these dots now? So we just follow from one to the other. So from angle 0 to angle pi over 2, the radius increases from 1 to 2. So as we're going from 0 to pi over 2, the radius must get larger. So let's fill that in. So from angle 0 to pi over 2, the radius must get larger up to the top. So must do something like that. Can you see the blue all right? Yeah. Then from pi over 2 to pi, so now we're going down the second quadrant there. It starts at 2, goes down to 1, so the radius must decrease down to 1. So it must be like that. Okay, and it goes down to 1. Okay, then what do we do in between? So we've got a radius of 1 here, we're at pi. Then 3 pi over 2, that's the angle going down. It must go from 1 to 0. So the radius starts at 1, And then when we get to the bottom line there, the radius must be 0. So it must look like that. Okay, starts out at 1, and as we go through, you see how it decreases down to the origin. Okay, and then from 3 pi over 2, so now we're at the bottom still, up to 2 pi, the radius then increases to 1. So we start at the beginning here, at the origin, and it's going to increase going out to 1. So it must look like that. Okay, so we end up with the following shape. Okay, something like that. Yeah, that's exactly what it looks like. It's called a cardioid. It's supposed to look like a heart, but not really much of a heart shape. But yeah, this is called a cardioid. Yeah. So if you're looking in the textbook, you'll see it under that section there. Right. Any questions on this one? Okay, not too bad. You get your points, and then you just connect the dots. Those that did the homework from last time, did you get the shape? No. Did you get something similar? Similar. Okay, well, that's good. Okay, yeah, the tutorial, I think there's like 20 practice problems that you can have a look at. All right, let's have a look at the next one, number 3. So this is r of theta is equal to 2 sine 3 theta. Okay. Okay, so we're going to do a quick sketch of the sine function, and then we're going to get our points, plot the points, and then connect the dots. So what's this going to look like? Okay, we see that the frequency there is 3. So from 0 to 2 pi, we're going to have 3 copies of the function. So let's draw now 3. So we're going to have 1, 2, and 3. So that's from 0 to 2 pi. And we can break it up into parts. So we have the first copy, second copy, and third copy, right? Again, because the frequency there's 3. So let's number our parts here. So that first bit, we're going to call that 1. There will be 1, there will be 2, there will be 3, 4, 5, 6. Okay. So each bump in the sine function, that will correspond to one part of the polar curve that we need to plot. Okay. Then some important points. Let's plot them as we go through. So the first one, obviously 0. Then at the top of the peak there, that will be at pi over 6. Okay. Next one, at the end of the first sine function there, that will be 2 pi over 3. Right, 2 pi over 3, because there's 3 of them. Then the next one, that will end at 4 pi over 3. Okay, and then the last one, that will end at 2 pi. Okay, so just some important points there. Now we're going to convert this into our polar curve. So we're going to start from our beginning points, 0, 0. Then we're going to look at pi over 6, and then 2 pi over 3, and so on. Okay, so let's draw in our lines. Okay, so these are going up in pi over 4s, going around. But we're going to be needing 2 more just in that first quadrant there, and then the others are just repeated. We're going to be needing pi over 6, so that's going to be somewhere here. Okay, so 30 degrees, we're going to put that in. And then in between pi over 4 and pi over 2, we're going to put in pi over 3. Okay. Okay, and then in between, that's our pi over 4. Okay. So we'll see once we've done with this first quadrant, then the other quadrants are just copies, okay, as we go around. So if you get the first bit, then it just copies over. Okay. And then this other line here, that's going to be 5 pi over 6. Okay, so we're just reflecting over there. Okay, so let's fill in our curve. So where do we start? Well, we start over here, angle 0, radius 0, so we're going to start at the origin. Okay, so we put a dot there. Next, at pi over 6, what value is this going to be? It'll be 2. That's at the top there. So at pi over 6, it needs to be 2 away from the origin. So there'll be over there. Okay, we can fill in our circles. So there'll be 1, there'll be 2. Okay, so there'll be 2 away. Next, once we're at 2, it's going to go back down to 0. Okay, so again, we start at 0, radius 0, then it's going to go up to radius 2, and then back down to radius 0. So just think about that. So it's 0, out to 2, back to 0. So let's try plot that. So it starts at 0, out to 2, and then back to 0. So it looks something like that. Okay, again, starts at 0, out to 2, back to 0. That's for this first bit, number 1. Okay, so here we've got number 1 there. Okay, then we look at the next one, and it's going to be the same thing. Okay, for the second part here, it's going to start at 0, out to 2, back down to 0. So it will be something like this. Something like that then. Okay, again, start at 0, out to 2, back to 0. Right, so that's for the second cycle, right? Because there's 3 cycles, frequency 3. And then the last one, out to 2, back down to 0. So it'll look like this. Okay, it will be something like that. Now, that's just to get the rough shape. If you want to actually sketch it going around, it will look something like this. Okay, so again, we start from 0. So I'm just going to put the arrows. Can you see the red? You can see. Okay, so we start from 0 out to 2, back down. So it's going to look something like that. Okay, so the arrows just show you how you're going to be connecting the dots. Okay, and then it goes around like that. Okay, so when you're sketching this at home, just again follow the points, and then you can see the arrows will help you with the plotting there. Okay, and then just homework. Cos 3 theta. So here it will have a very similar shape, but it will be rotated a bit. Okay, so again, just follow it. So you draw in your 3 cos graphs, but the cos graphs will start out at 1 and then go to 0. Okay, so the ordering of your dots will be a little bit different because you're starting out at 1, but you'll have the same sort of flower shape in the end. All right, any questions? No questions. Okay. And then in the tutorial, there's a few more examples like this. There's a sine 5 theta, and you end up with the flower shape with 5 petals going around. Okay. But you'll see that in the tutorial. Okay. Again, pretty easy to do. You just draw your graph. From your graph, you get your points, plot your points. Okay, again, whatever angle it is, whatever radius it is, you plot your points and then connect the dots. Okay. In the tutorial, there's about 20 or so practice problems to try. The solutions are already up, but please try it out first and then look at the graph, okay, just to make sure you know how to do it. Because as soon as you see the graph, you're like, okay, well, that's what it looks like, but you have no idea how to actually draw it. Okay. Any questions before we move on? All good. Okay. So next topic, vectors in polar coordinates. So you might have seen this in physics, or if you haven't, you will see it later on. So we're not going to be looking at this in terms of physics problems. We're going to be looking at this more mathematically. So where do these vectors come from, and how do we derive them? Specifically, the position vector. Okay, so we know the position vector in Cartesian system, right? Xi hat plus yj hat plus zk hat. What does that look like in polar coordinates? Okay, then the velocity vector. And finally, the acceleration vector. Okay, if you understand these three, you can understand all of the vectors in polar coordinates. And we're going to be focusing specifically on these three because that's heavily used in physics and engineering. Okay, so we start out with the position vector. Okay, so we know what it looks like in Cartesian coordinates. So we'll start with that and then convert it into polar coordinates. So this is position vector r is going to be xi plus yj. Okay. We're going to do this in 2D, just so we can do some plotting, but the same thing works in 3D. But there it won't be called polar coordinates. You'll either use cylindrical coordinates or spherical coordinates. Okay, that comes later. Okay, you'll see that next year. So here, 2D case for now. Next year, you'll look at the 3D case. Okay, so this is just in 2D. Okay, so how do we go from Cartesian to polar? Remember, x is r cos theta, y is r sin theta. So we're going to fill that in here. So x, that's going to be r cos theta, and y, that's going to be r sin theta. Okay, so we end up with that. Now, something very important to note is that since we're going to be dealing with this in physics terms, this is all going to be dependent on time, right? So if you have some particle moving around with a position vector, the position vector depends on time because it's moving around. The velocity vector depends on time, and so does acceleration. So just keep in mind that this position vector here will also depend on time. So we can write it as r of t. So the radius part, that depends on time. Cos theta of t, again, the angle can depend on time. I hat plus r of t sine theta of t j hat. Okay, so again, keep in mind all of this depends on time, but we're not going to write it like this every single time. So I'm going to just write r, right? But it means r of t. Okay, so just keep that in mind here. It all depends on time. Okay, so in Cartesian coordinates, back up here, we've got these unit vectors. You all know what unit vectors are. So I hat, that's the unit vector in the x direction. J hat, that's the unit vector in the y direction. We need the same thing for polar coordinates. So we're going to have unit vectors r hat. That will be a unit vector in the radial direction. Okay, and theta hat, we'll see what that is now. This is the unit vector in the angular direction. Okay, so what does that mean? Okay, so let's say we've got our polar coordinate system like this. At some point, let's say over there, we're going to have r hats that will be in the radial direction. So that's going to be going out like this. And theta hat, that's going to be pointing in the angular direction. What that means is the direction in which theta increases. So in our case, theta increases counterclockwise. So this needs to point counterclockwise. So it'll be like that. So it'll be theta hat. Now, if we pick a different point, we're going to have a different set of r hats and theta hats. For example, if we pick this point over here, okay, now r hat is going to be different. It's not going to be pointing to the right anymore. It's going to be pointing up. So r hat points up. And now theta hat no longer points up. It's now going to point to the left. Okay. So unlike in Cartesian coordinates where I hat and j hat point in the same direction everywhere, in polar coordinates, the direction depends on where you are. Okay, and we need to keep that in mind. Because again, for physics problems, when the particle is moving around, at some time the particle's over here, it's going to have some r hat, theta hat. At a later time, it will be somewhere else, and it will have a different r hat and theta hat. So r hat and theta hat depend on the point you're looking at. So r hat and theta hat depend on the point you're looking at. Yeah. And as the particle moves around, r hat and theta hat will also change. So what this means is that r hat also depends on time. Yeah, because as time goes on, particle moves around, r hat will change as you go. And theta hat will also depend on time. Okay, so that's a very important distinction between I hat and j hat, which are the same everywhere, doesn't depend on time. R hat and theta hat, they will depend on time. Okay, so what is r hat going to be? So the way we define unit vectors, I'm sure you've done that in the 132. So to define r hat, we take the vector r and we divide by its length. Yeah. So that is the definition for the unit vector. So whatever vector you're given, if you want to make it into a unit vector, you're going to take the vector and divide by its length. You're right. No. Oh, gosh. Do you need me to call someone?
All the time.
You sure? Oh, gosh. Someone, please go check. Thank you. Hey, this math is dangerous. Shit. Okay, so we have the whatever vector divide by its length, that gives you the unit vector. So position vector r divided by its length, that's the r hat. Okay, so let's see what that's going to be. So the position vector, we have that over here. Okay, the r cos theta, r sin theta. So let's write that out. Yep. So that's our vector. Divide by its length. You know how to find the length of a vector. So that's going to be roots r squared cos squared theta plus r squared sin squared theta. Okay, this simplifies down quite easily. So in the bottom, r squared, we can take that out. Cos squared plus sin squared, that's just going to be 1. And then at the top we have r, at the bottom we have r, that's going to cancel. Yeah, so that is the unit vector r hat. Okay, please put a box around that. Okay, so if that's the unit vector r hat, we can now rewrite our position vector in terms of r hat. So we got position vector r, that was r cos theta I hat plus r sin theta j hat. Okay, both of these have an r, so that can come out to the front. cos theta I hat plus sin theta j hat. Okay. But cos theta I hat plus sin theta j hat, we see from our box there, that's just r hat. So the position vector now becomes r hat. Yeah. And then please put a box around that as well. Yeah. So that is the position vector in polar coordinates, right? Because r, that's from the polar coordinates, and r hat, again, that's from our polar coordinates we just found. So this is the position vector in polar coordinates. Okay, now let's have a look at the velocity vector. Okay, so the velocity vector, that's just going to be the time derivative of the position vector. Right, that's standard stuff. But now we're not going to be using the Cartesian form because we want this in polar coordinates. So we're going to use that equation from that box there. So this is going to be d by dt of r hat. And again, the warning from earlier, over here, everything here depends on time. So we don't write it over here. We're not writing this as functions of time, but this is a function of time, and this is a function of time. So when we do the time derivative, we're going to need the product rule, right? Because it's a product of functions of time. So let's do the product rule. So we're going to do the time derivative of the radius r, and I'm going to write that as r dot. Okay, it's just notation, but it saves some writing. Okay, so that's going to be the derivative of the first term. We leave the second one alone, so that's r hat. Plus, and we leave the first one alone, and we do the derivative of the second. Yeah. Now we need to figure out what this time derivative is going to be. So that will be r dot r hat plus r d by dt. R hat, you're right? Okay. R hat, that's going to be what we have over there. So cos theta I hat and sin theta j hat. So let's fill that in. Okay. And again, that's a function of time. The theta is a function of time with the cos and with the sine. So when we do the time derivative, we're going to have to use the chain rule. So that's going to be r dot r hat plus r. And let's do the time derivative. Cos, that's going to become minus sine theta dot I hat plus cos theta dot j hat. Okay, both of these terms have a theta dot, so we can take that out. So this will be r dot r hat plus r theta dot minus sine theta I hat plus cos theta j hat. Okay, we end up with this. Now, what is that on the right there? What is minus sine theta I hat and cos theta j hat? This is, in fact, theta hat. Okay. And then figuring that out, that's going to be for homework. Okay, so the way we do that is we imagine we have a circle. Okay, a unit circle. So from the center going outwards, that's going to be r hat. Okay. Then theta hat, that must be perpendicular to that, right? So theta hat will be this vector here. Okay, so we have r hat going outwards. theta hat will be at right angles. So r hat, that is cos theta I hat plus sine theta j hat. Okay. If theta hat is at 90 degrees to r hat, well, we can just add pi over 2 to the angle, right, to make it 90 degrees. So theta hat, that will be cos of theta plus pi over 2, I hat plus sine theta plus pi over 2, j hat. Okay, so just simplify that right-hand side, and you'll get this in brackets here. Okay, and that will be theta hat. Okay, so let's put that in brackets here. So theta hat. Again, just simplify that. One line just to simplify that there. That's going to be minus sine theta I hat plus cos theta j hat. Okay, so that bit will be for homework, and there's your answer there. Okay, and then that gives us our velocity vector in polar coordinates. So the position vector just had r hat, but the velocity vector has r hat and theta hat. And we'll go over that in a bit. So the velocity vector, that was r dot r hat plus r theta dot theta hat. Okay, so this is the velocity vector in polar coordinates. Now again, the velocity now has two parts. The position vector just had r hat. This one has r hat and theta hat. The part that's connected to r hat, that is the radial velocity. So V subscript r for radial. This is going to be r dot. This is the radial velocity. Okay. And then the other one there, r theta dot, that will be the angular velocity. Yep. You may have seen this as r omega from physics. Okay. So omega, that was the rate of change of the angle. Okay. Radians per second or whatever. So theta dot, that is the rate of change of the angle. So you can write that as r omega for the angular velocity. Here we call it theta dot. Okay, so we've got the radial velocity for the r hat component and the angular velocity for the theta hat component. Right. Any questions so far? Oh, good. Okay, and then finally, the acceleration vector. Yeah, as we did with the velocity vector, we're going to do the same for the acceleration vector. So acceleration is just the time derivative of velocity, and we know what the velocity vector is. So we're just going to do the time derivative of that. So this will be d by dt of the velocity vector, but now written in the polar form. Okay, so let's see what that was. So r dot r hat, that's our first bit, plus, and then the second bit that has the three parts, r theta dot and theta hat. And again, I'm going to bring up the warning. All of that depends on time. R dot depends on time, r hat depends on time, r depends on time, theta dot depends on time, and theta hat also depends on time. All of it depends on time. Nothing there is constant. Yeah, so let's go through it one by one. So the first thing, that's a product of two functions. We got to use the product rule. So the derivative of the first one, that's going to be r double dot right, for 2-time derivatives, and then r hat. Plus, we leave the first one alone, and then the derivative of the second. So we'll just leave that for now. Plus, now we've got 3 things, so we need to do the derivative of each one. So the first one, that will be r dot. Then the next one, that will be theta double dot. And finally, the last one, d by dt of theta hat. Again, everything there depends on time. Let's have a look at the first time derivative there, the d by dt of r hat. We did that already over here. And we saw that d by dt of r hat over here was theta dot theta hat. So we can fill that in. Okay, again, that was theta dot theta hat. Plus, we can just copy the rest here. Sorry. Plus, and now this last one we need to figure out. So this will be r theta dot d by dt of theta hat, and we've got that over here in this box. So theta hat, that's minus sine theta I hat plus cos theta j hat. So let's fill that in. Okay, a few more lines and then we'll be done. Okay, so that's going to be, let's go back here. Okay, from this box here, minus sine theta I hat, cos theta j hat. Okay. And then we can do the time derivative, and remember, all of that depends on time, so we have to do the chain rule there. So let's just copy everything else. So r double dots r hat plus, we've got 2 of those, so let's put that together. Okay. Then we've got the r theta double dot there. Plus r theta dot. Okay, and then let's do this time derivative here. So the derivative of sine, that's going to be cos. Okay, and then we have minus sine theta dot j hat. Okay, now for that last bracket over there, the minus theta dot, we can take that out. So we end up with r double dots r hat plus 2r dot theta hat plus r double dot theta hat. That's going to be a minus. So the minus theta dot we're going to take out. So it will be minus r theta dot squared. And what we're left with is just the cos theta I hat and the sine theta j hat. That's left over. But cos theta I hat plus sine theta j hat, that's just r hat. Okay, we're going to do a little bit of grouping here. So this first term has an r hat, that last term has an r hat, so we're going to put that together. Okay, plus, and then those last 2 in the middle there, that comes with the theta hat, so we can put that together. Yeah, and that is our acceleration vector in polar coordinates. Okay, so the radial part, that's these first 2 terms. So that's r double dots minus r theta dot squared, r hat. And then the angular acceleration, that will be that second bracket there. Okay, and that's the last thing for brackets. And like we said with the velocity vector, there's going to be two parts. So the radial part, we call the radial acceleration. So A sub r. Radial acceleration. Okay, and then the one with the theta hat, that is the angular acceleration. Okay. And then just a little extra thing on this first part here with the radial acceleration. Okay, so remember mass times acceleration, that's your force. So if we take this first part and multiply it by m, that will give us a force. So m r double dot, that will be the radial force going outwards. So this is F equals m r double dot. Okay. And then the second part here, that comes with the minus sign. So it's going to be pointing the other way. So this will be F equals minus m r theta dot squared. Or you might have seen this as minus m r omega squared. Okay, so for a particle moving around in a circle, you're going to have the one force vector going outwards for this first part here, that comes with the plus sign, so the force is going to go outwards. And then the second part, that comes with the minus sign, so the force goes inwards, and we call this the centripetal force. Okay. So I think you've seen it like this before in physics. Okay, the centripetal force going inwards. Okay. Then for homework, what is this part over here? Okay, so r theta double dot, that's just your angular acceleration going around. But 2r dot theta dot, what is that in terms of physics? What's that going to be? So this one is your centripetal force. What's this one over here? So homework, what is just this part here, the 2r dot theta dot? What is that in terms of physics? Yeah, so what is that going to be? Okay, any questions on these derivations? No questions. Okay, please make sure you know how to derive these three. So position vector in polar coordinates, velocity vector in polar coordinates, and acceleration. Okay, you need to be able to derive those three. Any questions before we go? You're good. Okay.